What if the dataset contains different intervals of the independent variable? Is there an effect in the determination of the function? Check it out here in Numerical Solutions to see problems. The approximate approach of curve fitting needs to minimize the errors, if not zero it out. And with this method, the concept is to have the positive errors balance out with the negative errors so they can cancel out. The definite algorithm of group averages starts by dividing the dataset into two tables. In case there is an excess pair of coordinates, the first table would absorb it. Next is to take the summation of the x and y values in order to solve the average of each variable. Having an average x and y values, place them into the slope-intercept format of a linear function. Then through simultaneous equations, solve for a and b. Then again, these variables are placed into the required function. The dataset for this case contains 9 points and the x intervals are irregular. Nevertheless, the process of regression remains the same, so the dataset is divided between x of 2.5 and 3.2, making the first table with 5 coordinates. If we add all the x values, we get a total of 6.7 and y has a total of 81.32. For the second table, x total is 18 and y total is 252.93. The average is taken by dividing the total by 5, giving x of 1.34 and y with 16.264 from the first table. Divide the total by 4 for the second table, thus giving 18 over 4 or 4.5, and 252.93 divided by 4 as 63.2325. The partial equations are then generated. The first is 16.264 as equal to 1.34a plus b. Then the second table gives 63.2325 as equal to 4.5a plus b. With the two equations already known, solve the variables with simultaneous equations function, or simply subtract them, making negative 46.9685, and this is equal to negative 3.16a, where a is then 14.86345. Plug this value of a into the other function. Say we use the first, giving 16.264 as equal to 1.34 times 14.86345 plus b, which yields b is negative 3.65302. So the best fit line for the dataset has a function of y as equal to 14.86345x minus 3.65302. When working with the function of a quadratic curve, identify if there is a special point of interest, where in this example, it is the point with coordinates 1.2 and 12.45. After clearly showing this point, the third and fourth columns can be given functions, where capital X takes x plus 1.2, and capital Y is equal to y minus 12.45 all over x minus 1.2. Complete capital X values is starting with 0 plus 1.2, which is 1.2. Then do the same with the rest. Next is for the column of y, where the initial value is 0.1 minus 12.45 all over 0 minus 1.2, and that is 10 0.29167. Do the same for the rest, but then take note that the third point is the one in our interest, which eventually will come out as undefined, so take it as 0. Next is to take the total of the last two columns. So capital X has a total of 12.7, and capital Y is summed up as 48.96811. Their averages are taken by dividing the total by 5. So capital X turns into 2.54, and capital Y is 9.79362. The first equation is then generated as 9.79362 as equal to 2.54a plus b. Table 2 has x values from 3.2 until 6. Capital X is then x plus 1.2, giving the following values. Capital Y is also computed using the derived ratio. Again, take the total where capital X turns to be 22.8 and capital Y is 59.83652. Their average is solved by dividing the total by 4. So capital X is 5.7 and capital Y is 14.95913. This then gives the second function of 14.9513 as equal to 5.7a plus b. The two functions from each table are then subtracted in order to have the values of a and b. The difference gives negative 5.16551 as equal to negative 3.16a. So dividing the result by negative 3.16 gives the value for a, which is 1.63465. Plug a into any of the equations. Again, we take table 1. So the function turns as 9.79362 as equal to 2.54 times 1.63465 plus b. B is then taken as 5.64161. With a and b already known, we then solve for the value of c. The equation to use is from the quadratic equation with the point of interest, making the equation 12.45 as equal to a times the square of 1.2 plus b with 1.2 plus c. Also substitute a and b into the function to have 12.45 as equal to 1.63465 times 1.2 squared plus 5.64161 times 1.2 plus c, which makes c as equal to 3.32617. And there it is. The best fit quadratic curve has the function y is equal to 1.63465x squared plus 5.64161x plus 3.32617. If instead of a quadratic curve, we look for the best fit exponential curve, and that is by having two tables similar with the previous ones, but this time an additional column for logarithm of y is attached. The logarithm of 0.1 is negative 1, and the rest is solved by simply taking the log of y. Next is to take the total of x, which is 6.7. The total of y is 4.0523. The average is then also taken where 6.7 over 5 is 1.34, and y average is taken as 0.81046. The first equation is then 0.81046 as equal to 1.34a plus b. The second table is filled out similarly, where the third column has capital Y, which is the logarithm of y. Taking the total, x is added together to have 18, and capital Y becomes 7.1133. 1.11326. Take their average, that is 18 divided by 4 is 4.5, and 7.11326 divided by 4 as 1.77831. The second equation is then 1.77831 as equal to 4.5a plus b. Solve for a and b simultaneously from the two generated functions, and that is through subtraction, where we get negative 0.96785 as equal to negative 3.16a. A is then solved as 0.30628. This is capital A, and A is Euler's number E raised to 0.30628, giving A as 1.35836. Use A to solve for B from any of the equations, say using Table 1. The function then is 0.81046 as equal to 1.34 times 0.30628 plus b, giving b as 0.40004. b is then raised to 0.40004, where it is solved as 1.49188. So the best fit exponential curve for the dataset is 1.35836 raised to x multiplied by 1.49188.